Okay, my screen is visible, right? Okay. Okay, so everyone, so hi everyone. Today we will discuss some topics in elementary number theory. So today's session will be a very interactive one. So feel free to unmute and ask questions, make any comments, or like answer questions, anything. So let's dive into the topic. So can anyone say what is like the topic number theory? Does anyone have any idea of number theory? What is number theory? Any guesses? Any suggestions? Okay. So number theory is basically the study of uh, integers, and you may say integer valued functions. Okay, so this thing is visible, right? Can anyone please confirm?
Yes, sir.
Okay.
Yes, sir.
Yeah, no problem, sir. Okay, so after that, so basically we will be talking about prime numbers, divisors, factors, multiples, and all the stuff that are specific to integers. Integers, in some sense, we can also generalize the facts to rational numbers, but for real numbers, we would be rarely touching them. Okay, so just now, like for now, we will be focusing just on integers, positive and sometimes negative. Okay, so let's start with some basic notations. So starting with this notation, I think everyone knows what this notation is. Can someone say what this is?
Natural
Anyone?
number.
Yeah, so it's the set of natural numbers. 1, 2, 3. A very related set to natural numbers. Anyone? Can anyone say what Z is?
Whole number. That integers. Integers.
It's all integers. Uh, okay. It's from -2, -1, 2, all of them. So these are the two sets we will be looking carefully today. And there is some other notations that I would like to define. So does anyone know what this notation means? Let's say A, this vertical bar B.
A divides
A divides B. That is, B can be written as a multiple of A, right? Where this K is an integer. Okay. So any doubts in this portion? I mean, these are just definitions, but still. Okay. So I guess we can move on to uh, modular arithmetic right now. So, Acha, by the way, can you guys raise your hands? Just those of you know about modular arithmetic, or at least heard of it.
Can you give an example?
Uh, okay. Yeah, I'll go to modular arithmetic, but yeah. Okay, so not too many people know about this. Okay. So basically, in modular arithmetic, we define a notation like A is okay. So I'll read this out later on. So I'll just write it initially. So we write some fancy thing like this, okay? And this is read out as A is congruent to B mod n or modulo n. This is a fancy way of just writing that A leaves the same remainder when divided by n as B would do. So basically, if A is divided by n, so you will have something like this, right? This is the quotient and this is the remainder. And if B is divided, sorry, it would have a different quotient and it would have a different remainder, where this R1 and R2 are between 1 and n, 1 and n minus 1. Then it means that R1 is equal to R2. So this is the definition of this. Or in other words, you can also say that A minus B is a multiple of n, or n divides A minus B, right? Please convince yourself that this definition, where R1 equal to R2, is equal to this definition. So any doubts in the definition? Is it clear? Okay, I think there are no doubts. So for I'll give some examples. Let's do some examples. So we can write something like 5 is congruent to 12 mod 7. Can someone say why? Anyone?
Both leaves remainder 5 when divided by 7.
Yeah, both gives remainder 5. Or you can say something like 5 minus 12 is a multiple of 7. By the way, is my voice clear? Because there is a power fluctuation over here.
Yes, clear.
Okay, sure. Similarly, we can write something like 2 is congruent to, let's say, 2 itself, mod 5. Right, this is a pretty obvious thing. Let's get some space. We can also write stuff like minus 3 is congruent to 2 mod 5. Can anyone say why this is true? Why can we write this?
If we multiply 5 by minus 1, then we get remainder minus 3.
Sorry?
Minus 3 minus 2. So it's minus 5. And it's
5 into minus
modulo.
1.
If quotient is minus 1, then
Okay,
remainder
5
will
into
be
minus 1
minus 5 plus 2 is equal to minus 3.
plus 2 equal to minus 3. And 5 into 0 plus 2 is equal to 2, right?
Yeah.
So this is R1, this is R2. So R1 equal to R2. And someone else also correctly pointed out minus 3 minus 2 is minus 5, which is divisible by R1, which is equal to minus 5, which is divisible by 5, right? Sorry, which is equal to minus 5, which is divisible by 5. It's clear, right? Hello?
Yes, it's clear.
Yeah. Moving on. We can also write something like 27 is congruent to 0 mod, let's say 9. Right? This is obvious, right? In fact, any
Yes.
factor of 9, 9 into 1001 is congruent to any other factor of 9, 777, right? Because the remainder over here is 0 and the remainder over here is also 0. This is clear, right?
Yes.
Okay. And just for a final example, I'll just state that 102 is congruent to, let's say, 712. Mod n. So you can see that dividing this gives you a remainder of 2 and dividing this gives you a remainder of 2. So it's nothing. Okay. So now everyone's clear with the definition. By the way, some of you might have already realized this, but basically what this does is, if you fix the value of n, then this like fancy thing that you write a comma b, a is congruent to b mod n. This thing actually gives you an equivalence relation on z, right? So everyone should know what an equivalence relation is, right? Is there anyone who doesn't know? I think it was in J. Okay, I'm assuming everyone knows. So you can just prove it, like it's reflexive, it's commutative, and transitive. So for example, we call, let's say we take n equal to 7. Then the equivalence class in which 3 belongs is equal to all the numbers of the form 7k plus 3, such that k is an integer. So we write it something like this. Any questions? Okay. Okay, so basically now you understand that this gives you an equivalence relation. And since an equivalence relation partitions the set in which you are getting the equivalence relation from, so you can basically partition the set of all integers z into some finite number of equivalence classes. So for example, if you have 7, so you can partition this 7 into all integers of form 7k plus 1, all integers of the form 7k plus 2, blah, 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 all integers of the form 7k plus 6, right? So this entire thing gives you the entire set of integers. So for any integer you take, you can place them exactly in one of these sets, right? Okay. Now let's move on to what the CP questions mainly want you to do. So in CP questions, you will get something like this written. So print s the value. Print s the value of the required sum for some question, modulo 1e9 plus 7. So what this means is, you need to provide the value of s. You need to provide the value of the remainder when s is divided by that number, divided by m. M. Here m equal to 10 to 9 plus 7. So here we can write any number in the right hand, in literally any of the sides. So if it's 102, we can write 712, we can write 1712, we can write anything ending with a 2. But what they want us to do is report nothing but the integer 2, because when you divide 102 by 10, you get the remainder as 2. So this is a unique number, right?
Yeah.
Okay. So what they want us to do is report this R such that this holds. R is between 0 and m minus 1, right? So this is
Sir?
basically the remainder. Were there any questions?
Sir, I have seen that in many programs they ask output in terms of modulo this number 10 to the power 9 plus 7.
Yeah.
Sir, what is the logic there?
What is the logic in asking the answer modulo something, or what is the logic behind choosing such a absurd looking number? What is the question?
Yes, sir. Choosing such a that number. Absolutely.
Okay, so there's a certain thing about like 10 to the 9 plus 7. For like the main important thing is that this number is a prime number, so you can check that it's a prime number, and the modulo which you are asked, if that's a prime number, then you can do certain stuff that we would discuss later on, if time permits. That's really helpful. So being a prime is really helpful, and this is a large number, so yeah, that's a part of the, like, it does provide a better, how do I put this? So it does provide a better way of checking your answer. So if this was a low number like 2 or 3 or something, so by 1/3 probability, if you guess something randomly, you would get it correct. But with such a high number, you literally can never get it correct by guess. So you actually need to solve the problem. Does that more or less clear the doubt?
Yes.
Okay. Okay, so I think everyone knows about this percentage operator in C. This was done in your PDS class, right?
Yes.
Yes, sir.
Okay. Yeah, you don't need to call me sir. I'm Anubhav. Yeah. Okay. So what they want you to do is basically find this answer, right? Now there are some interesting properties that hold for this operator. So I'll just start with some property out of the blue. So this value is actually this value. Okay, so it might be pretty obvious to some, but like, can you rigorously prove this thing? Anyone? Okay.
We can take P as some m k plus n,
Okay.
and then Q as similarly m into k2 plus n. Uh, Now we can substitute in both sides, then it will give equality.
So it's just n plus n, m times k plus k2 plus n plus n2 percentage n. Yeah, sorry, is equal to, so this is n and this is n2, right? N plus n2 percentage n. Yeah, that's totally fine. So the key observation is multiples of m are ignored in the modulo operator, right? This is pretty obvious. Okay, so basically you get n plus n2 percentage m on both sides, right? So yeah. Okay. Similarly, can you prove that if you multiply first and then take modulo m, this would be same as, sorry. Okay, I should refrain from using curly braces if I'm writing C style codes. Okay. So this is sort of also pretty clear, right? Can anyone say why this is true?
Same logic as previous one.
Same logic. So this will be mk1 plus n, sorry, mk plus n, mk2 plus n2. So only the n into n2 part would remain and others would be divisible by m. And here also you have n into n2 part. And yeah, so both sides would become n into n2 percentage n. Also, can anyone say what would be the problem if I had not put this percentage n over here?
The sum may be even divisible by again m.
Yeah, so basically, yeah, so what you said was totally correct. So this sum can actually have a range from 0 to 2 into m minus 1, right? This can
Yeah.
be from 0 to m minus 1, this can be from 0 to m minus 1. So the entire sum can have a range of 0 to 2m minus 1. So you just want this to be in range 0 to m, 0 to m minus 1. So yeah, you do need to take a third modulo for this. Similarly, over here, you can't just forget about this modulo. This is important. Anyway, so convince yourself that you can actually do something like this as well into q percentage, right? These are all pretty clear. Okay, now coming to subtraction, p minus q. First of all, I'll just put something. So, does anyone know what's going on over here? It's actually not always equal. This is not a mathematical property. This is a property of the C language. So, does anyone know about this? Okay.
I think it must be modulus of p% by m minus q% by m.
Sorry, modulus of
Operator
Modulus.
positive numbers, I guess.
one at a time. One at a time.
The operator takes positive numbers, I guess.
Yeah, like it's like you are close. Basically, for negative numbers, it gives a negative modulus. So when I said this thing that they actually want what you get by percentage, I actually lied for a small portion of the cases. So basically, you need to make sure that this argument is positive. Okay, that is very important.
Yeah, like we can use modulus, no?
So
Mod of p minus q.
mod of p minus like this.
He's saying modulus.
Mod
Absolute
He's
value.
saying
absolute.
absolute.
Oh,
Yeah,
absolute value. Okay. Okay. Percentage n. Is this what you're saying?
yeah.
Okay. There is an issue with this, so basically, let's try to construct. So let's say P is 1, Q is 4, and M is equal to 5.
On the left hand side also we should
Sorry?
take modulus, no? On the right hand side also we should take modulus, no? I mean the absolute value.
This part.
In the RHS, p% m minus q% m.
Oh, yeah. Okay. So you are saying this fact is true, equal to modulus of this thing. Is this what you're saying?
Yeah, I think that's correct.
Okay. Make it 6 and check. So what is p minus 4 percentage m percentage 5? This is 2, right?
Yeah.
And this is 1, 4, 5. This is minus 4, minus 3. Sorry. This is 1, this is minus 4, so this is minus 3. So the entire thing is plus 3 because you've taken the absolute value. And then you're taking modulo 5, so it gives you 3 back. So if I'm not doing some arithmetic mistake, so this is also not always true. Right?
Yeah.
Okay, so anyway, my focus is to somehow find this value. So like when you have a number p and another number q, and they want you to find the value of p minus q modulo m. So it's written in the problem statement of your problem that you're handling. So how do you do that? By making sure that the argument is always positive. Any guesses?
We can add m on the right hand side.
Yeah.
Oh, right hand side of this.
Yes, like
Okay, so
m,
can you please like tell me what you're thinking?
like absolute value of m plus p% by m minus q% by m will always give
P
correct value.
percent m minus q percent m.
Yeah, modulus.
M, this thing.
No. M, yep. Like inside the upper absolute value m plus p% by m minus q% by m. Like
Like
we
this.
will add m to the expression. Yeah.
Now you are taking percentage m again.
I think mod is unnecessary here. We
Mod is
can
unnecessary. Exactly. Mod is unnecessary. Because this value is positive. This value can be at most m minus 1. So this minus this is also positive. Right.
Yeah.
Okay, so the assumption is p and q are positive. So yeah, I should have stated that, but yeah. So this mod is unnecessary, and you must take another mod over here, right? Because what if this is 0 and this is also 0? Then if you don't take this mod, then you end up with m. So whereas you need an answer of 0. Is that clear for now?
Yeah.
Okay, great. Okay, then so I've talked about plus, multiplication and subtraction. Let's postpone division for some time because division is a lot harder to talk about. So I've just put in some examples with how problems are like how problems want you to print the answers. So here you see some stuff are given over here, and you need to print this thing modulo this. So for example, if your answer is 10013 and you are asked to print it modulo 200, then you print 30, right? Makes sense, right?
Yeah.
Okay. So this is just a brief recap. Now I've given some examples of things that you should and you shouldn't do. So basically, these are very important points. These are very important. Yeah. So these are very important points. Use long logs. Why would int not suffice? Can anyone say? So does anyone know the limit of int for C or C++?
Some 32,000.
Or
That's
16 minus 1. 2 per
2 power
15 and 2 power minus
minus
2 power 15 to 2
To
power
the power 31 minus 1 for signed integers.
yeah. So this used to be the upper limit for integers well back. I think in the 20th century, but like for more like today's C++ 17 or stuff, even for C's nowadays, I think it's 2 power 31 minus 1, right? Hello? Am I still connected? Yeah. Yeah, so this is the limit of int that you would be handling with in competitive programming problems. Now, this value is certainly greater than 1 in 9 plus 7, right? Just check once this is some. It's of the order 10 to the 9, but it's slightly greater than 10 to the 9 plus 7. So, when you are taking modulo for each step, let's say if you are taking modulo p plus q, and then when you add something to it, p equal to p plus q percentage m. So in each step, if you are taking modulo, so this value is guaranteed to be less than 10 to the 9 plus 7. Hence, it is guaranteed to stay within the limits of n. So why do we need to use log nodes? Can anyone point out where ints might be problematic?
p plus can be greater than int.
Exactly. So when you are performing this arithmetic operation, this value can overflow. And if this value overflows, bad stuff would happen. Okay. So always use long nodes. Again, so addition is a relatively civilized example. If you take multiplication, this thing can literally blow up to 10 to the 18. Right. So this is 10 to the 9. This is 10 to the 9. This entire thing can blow up to 10 to the 18. And then you are computing modulo again. Right. So you need to use long. So long is a must. Also, you should take modulo at each step. So let's come to this example one that I've put over here. So over here, I think we just want this summation of I equal to 1 to n, sorry, 0 to n minus 1. Ci. So we just want this value modulo some number. So can someone point out what the mistake is in this part?
Some will exceed.
Yeah,
the
so
limit
this
value.
sum will exceed the integer or even the long integer part, long integer limit very quickly. So if the values of, well, not long integer thing, but definitely for ends. And also I've used int over here, which is like, as I said, you must always use long ones. And yeah, so you must take modulo at each step. So here I've substituted the longs with int with the long, and I've taken the modulo at each step. And as you can see, this modulo is not really relevant right now. So it doesn't change the answer, right? I hope that's clear.
Yes.
Okay, so you should do this. This is a good practice. And maybe for this example, it won't blow up to 10 to the 18. But if you have a multiplication over here instead of addition, then it would definitely blow up very fast. After 3 numbers, you are talking about ranges like 10 to the 9 into 10 to the 9 into 10 to the 9, which is 10 to the 27. So that is all. So everyone knows the limit of longs, right? It's around 9 into 10 to the 18. Sorry, 9, yeah. It's around 9 into 10 to the 18. So as you people might know better, it's something like 2 to the 63 minus 1, I guess, right? Just check this.
Yes.
I'm not very sure.
Yes.
Okay. So if this was a product, then there would be problems in here as well as here. Okay, so moving on to the next example and the next point that I was talking about. Take care of negative values very carefully. So this part where I said that p minus this thing can be negative. This is a very, very common source of wrong answers in computer programming problems. So over here, you can see I've done some programs where I have answered summation over ai, bi, ci, ti. And over here, I have something like summation of ai minus bi plus ci minus ti, right? So I've taken this assumption that every values of a to d are within the range 0 to mod minus 1. But there are still some problems over here. Can some of you tell? Well, it's already visible over here. So basically what happens is this thing can overflow, right? Yes, no, not clear. Any response? Hello?
Yeah, like here, what is CI?
What is ci?
Yeah.
Okay, these are some values that you have. You just want to find out this value. ai into bi, summation over all I, ai times bi times ci times bi for some given arrays of integers a to d.
Okay.
Okay, so please speak up if things are not clear. Otherwise, these will build up in later parts as well. Okay. So here, this value can easily overflow. So if this is of the order 10 to 9, if this is of the order 10 to 9, if this is of the order, these are all of the order 10 to 9. So this can be very large. So what you need to do is you need to take care of this very carefully. So here I have taken 2 at a time so that the number stays in the range 10 to the 18, which is in the range of long n's. And then I've taken a modulo. So this entire number is of the range 10 to the 9 again. Similarly, this entire number is of the range 10 to the 9 again. And then you multiply those up, then you get a number of 10 to the 18 range, and then you add to the answer. You can also take another modulo after that, but it's pretty safe if you do this way. Similarly, over here, you can see that there are two sources of negative numbers, right? As I talked about earlier over here, that you need to add n. So since there are two sources of negative numbers, your entire sum might be something like -2 into mod. Well, not -2 into mod. It can get as low as 2 into mod -1, -2 into mod -1. Anyway, the point is that you need to incorporate a 2 factor over here and add it to the total answer so that the entire number remains positive. So this part and this part, these two cancel out their negative contributions with this. And this is positive, this is positive, this is positive. So the entire thing stays positive and you can happily take it. So I hope this is clear as well. Okay. Any questions? Okay. I hope no. Okay, so now let's start talking about prime numbers. So everyone knows what prime numbers are. Can someone just tell the definition of a prime number?
A number which has factors 1 and itself.
A number with factors 1 in itself. That's right. With only factors 1 and itself, right?
Yeah.
So here I think you should use the word 2 factors only to exclude 1 as a prime, right?
Okay.
Yes. So you have 2 distinct factors, 1 and itself. So some examples of primes are 5, 7. You know better than I do probably. And some example of composite numbers are 9, 27, 30, etc. I mean, I'll use this example later on for working programs by hand. So I'll just do this. Anyway, so now we will be talking about this problem. This is a very simple problem and a very elementary problem. This is probably the second or third thing that you learn while learning programming. So this is the problem. Given a number n, assume n is greater than 1. Check if n is a prime or not. So how do you do this? I've given a code over here, but if anyone would like to tell.
Like then checking for the whole I less than, and we can stop it I less than root n.
Okay. Okay, I see that we are ahead of what I was trying to explain. Anyway, so here we are just iterating over all elements in the range 2, 3 up to n minus 1 and checking if any of this divides n. So I think everyone knows this, right? So just a quick check. If anyone has a problem, you can unmute now, I guess, for this part of the group. Okay, so if nobody has a problem, I can ask a question, I guess. So you all attended the last lecture on complexity theory, right? So can someone tell me the complexity of this program? The time complexity of this program?
N.
Big O of n, right?
Yeah.
Why? Because
you have to go through 1 to till 2 to n actually.
yeah, so because in the worst case you need to go from 2 to n minus 1 all of them, right? So this is an order n algorithm, but and this. So someone said something with root n, right? Can you tell me why root n is sufficient?
They are just complementary after that. The factors.
Yeah. Okay. So basically so let me put it in a different way. So if n is a prime, then it has no other factors other than 1 and n. Otherwise, if n is not a prime, then it has some factors a and b such that this holds, right? Okay, you can assume this holds as well. So for a composite number n, this is true. Everyone agrees, right?
Yes.
Is a is actually less than square root of n. That's right. The normal math way. So can anyone see why? Anyone?
Root n into root n is n. So after that, if the factors are increased, then it will exceed n. Like something
That's perfect.
similar
That's
to that.
So root n into root n is equal to n. And then since b is greater than equal to a, then root n must lie somewhere in between over here. So a must be less than equal to root n and b must be greater than equal to root n. So yeah, that's a way of realizing the fact. Maybe you can rigorously prove this by assuming that, okay, a is greater than root n and then see what happens. So since b is greater than equal to a and a is already greater than root n, so b into a is greater than root n into root n, which is equal to n. So a into b is greater than n, which is false. So this is false, so this must be false. So we have narrowed it down to root n. So that actually provided this code. So instead of writing square root n, I is less than equal to sqrt n. I chose this way of writing just because sqrt is handling with real numbers, whereas I want to handle with integers. And handling real numbers is not always a very safe thing. So for example, if you try to find the square root of, let's say, 10 to the power 18 minus 1 and then assign it to some int, it is, I think you will get j equal to 10 to the power 9. So it doesn't give you the floor exactly because of floating point errors and all. So I just chose to stick with this integer way of handling this. Okay, so coming back to complexity, what is the complexity of this program?
Under root n.
Big of root n, right? Okay, so can anyone tell me if n is equal to 10 to the power 18? Can I run this program? In a competitive programming environment? Anyone?
I think we can.
Come on, we covered this in the last class.
No.
It's a bit risky because you have modular operations and big O of root n is of the order 10 to the power 9. And you have costly operations like this. So it's a bit risky, I would say. For 10 to the power 18 over here, it would never work. That is very clear, right? It would take literally 10 to the power 7 years or something. I don't know.
Yeah.
But here you do have a chance. But okay, usually problems don't have this high numbers for primary testing. But numbers like 10 to the power 12, 10 to the power 13, these kind of numbers can easily fit over here, right? 10 to the 12 order root n is 10 to the 6. So this is well under the approximate limit that we had. So 10 to the 6 is fine. So 10 to the 12, 10 to the 13, stuff like that can be handled by this code. But in this code, you can't handle them because order n gives you 10 to the 12 for numbers like that, which is well above 10 to the 8. This is clear.
Can we do something like we take the first 10 prime numbers and after that we just check if integer is divided by that?
Can you please repeat? Can you please repeat?
Can we just take the first 10 prime numbers?
First 10 prime numbers.
Yes, and then for the numbers greater than that, we check if the number is prime or not, and if the number is prime, we add it to this list.
Okay, so what we are doing is brute force the first 10 first 10 primes, right? Then what is your algorithm?
Then for any integer greater than the last prime number here, we check if the number is divisible by any of these 10 primes.
So for example, if you're given an integer like 67, Then you check if 67 is divisible by any of these, right?
Yes.
And
Well, actually, I was thinking of something like we start from the integer next after this last prime.
okay.
So that
So
would generate a list of the prime numbers.
okay. So basically, you have some algorithm like brute force 10 primes, first 10 primes. Then start from the next number. Let's say p of 10 is the 10th prime, and then you start from this number. And what do you do with this number?
Check if the number is prime and keep on increasing that.
How do
And
you
once
check if this is a prime?
we divide it with the 10 in primes that we already have.
Okay.
And if it is divisible, it is not a prime, but if it is not divisible, then it is a prime.
So if it is a prime, then
It is not divisible by any of these 10 primes.
yeah. So you got the result if q is a prime and q is not a prime. After that, what you do?
After that, we add it to the list.
If it is
Like,
prime, right?
yes.
Okay, that's a much better algorithm. So can you tell me the complexity of this algorithm? If q is a prime.
It would be pretty much less like we take any integer, like this won't check for any arbitrary number. It would go on like starting from the number q.
Okay.
So we would first have to collect the prime number nearest to the number given.
Number given is n.
Yeah, if the number given is n, we would have to calculate a q nearest to n.
Nearest to n or nearest to root n would also do.
Maybe nearest to n.
Okay. I think nearest to root n would also do, right? Because of this, that if n is a prime, then it doesn't matter. If n is not a prime, then you will be having a factor which is less than root n. And since this factor itself has at least a prime divisor, so you will have a prime divisor of n which is less than root n, right?
Yes.
So running up to root n would do. But
Yes.
would it be a better algorithm finally? So for each I from, let's say 17, 18, I think 17 is the time. I don't know. Maybe up to 17 you can compute all the primes. And then you run up to root n. For each of these numbers, you check if this
No,
is
no,
a
no, no,
prime.
no. Once we calculate q, we start from q plus 1.
Yeah. So basically, I'm just saying that if this is q, you see that this is not a prime. Okay. So you move on to 19. You check q. Okay. Then you see this is a prime. Like this, right?
Yes, yes.
Yeah. So there are order of root n numbers over here. And for each prime checking, you can have. Okay, I don't want to give you the estimate right now. So basically, there's a theorem that the number of primes less than a given number n, so people call it pi n. This is actually order of n by log n. This is the number of primes less than n. So if you check for all of these, so if n is over here for some value, so for each of these checking, you will get something like order of q by log q. And since q can have values from 18 to root n, on an average, it would have something like 18 plus 2 value for q, which is order root n. So you would have something like order root n into root n by log root n, right? Root n from this root n by log of root n from this. So which is basically n by log n. This is not, I mean, this is a great way to find another algorithm that I would be discussing with you in a couple of minutes. But yeah, the problem is the complexity is not as good as order root n. So is that clear?
Yes, yes.
Okay. So like, this is a very hard theorem. Like, I don't think I can even understand the proof of this right now. Anyway, I'll be moving on to another, let's say, optimization. So here I have stated a fact. Can anyone prove if this is, can anyone prove this to be true, or can anyone come up with a counterexample? Any suggestions?
6k plus 4, 6k plus 3, and 6k plus 4 are always divisible.
6k plus 4 and 6k itself. So these are the only 6 kinds of integers that you can find. So this is divisible by 2, this is divisible by 3, this is divisible by 4. Sorry, this is
2.
divisible by 2 again, and this is divisible by 6. So all of these are composite numbers. So checking only these are enough. And you know that 2 and 3 are primes. So in fact, 6k, 6 into 0 plus 2 is divisible by 2, but turns out that that is the smallest number that is divisible by 2, hence it's a prime. Okay. So I have used this fact to compute a program. So if n is 2 or n is 3, you return this to be true. Otherwise, you check if 2 or 3 divides this number. If yes, then you know that this number is not a prime. Otherwise, you start from 6 until root n, as you did, and you increment 6 by each time, and you check for I minus 1 and I plus 1 if they are, like, if they are factors. So isn't it a much better program compared to this one? Yeah, this seems to be lengthier in terms of lines of code, but here you are actually checking with only, let's say, root n by 3 number of candidates, right? So this program is actually 3 times faster. Not exactly 3 times faster, but you get the point, right?
Yeah.
Okay. So what is the complexity of this program then? Anyone?
Root n?
Okay, so is it root n or order root n by 3?
Yeah, root n by 6, I think, or 3, something like that. But finally, it is root n, no?
Exactly. This doesn't, like, these two are basically saying the same thing. You don't care about the constants that are in the term, right? So order root n is same as order 1.56 into root n, anything, right? So you don't care about this constant factor. So yeah, the order root n is correct. So complexity wise, this and this are same, right? But this does provide a constant optimization. And by constant optimization, I mean that this constant factor that used to be here, this gets out optimized. Okay. Any doubts over here? Okay, I assume everything is clear. So I'll move on to the next variant of primality testing. So you are given Q numbers. We often call this Q queries in terms of programming terminology. So you are given Q numbers. Let's say you are given P1, P2, PQ. And for each of them, you need to find whether this is a prime or not. So any algorithm that comes to mind? Anything? Okay, forget about this one now. The numbers are in this range, and you want to find for each number if it's a prime or not.
2, 3,
Like we'll give
6k minus 1, 6k plus.
Okay, there were 3 answers, but I didn't quite get any of them. Can you please repeat one by one?
we'll use 2 for loops. One will be like the you means for going throughout the array, and another will be for checking primality of each number.
Okay, so you basically check for each check primality for each number, right? Each query. This is what you are suggesting, right?
Yes.
And how do you check?
Using the previous algorithm of checking prime numbers.
In order?
Root n.
In order root n.
Yes.
Okay. So the entire complexity of the program would be?
N power 3/2.
Okay, it's like Q into root n. So like I'm assuming that the numbers given are n and the number of queries Q. Okay, so maybe I should write it this way. So if the numbers are pi, so this would be order pi, right? Order root of pi.
Yes.
So this would be order of summation of root of pi over I, which we can roughly say that order p, where p is equal to this number, let's say. So every prime must be less than or equal to this. So this part makes sense, right?
Yes.
Okay, now someone was suggesting using this 6k plus 1, 6k minus 1 algorithm, right?
Yeah.
Yeah, so complexity wise, it would be the same.
Huh.
Anyway. Okay, so I'll be talking about another algorithm, which I think many of you have learned in school well before J. But let's see if anyone remembers. So the basic idea, so the algorithm is called sieve of Eratosthenes. So how many of you know this name by raise of hands? Okay, not many people know about this. Okay, so I can talk about this algorithm also. So what you do is you initially, like, you know that one, so you have a grid of the numbers that you want to find out. You basically have some way of writing this numbers of the range. So instead of 2 to 10 to a 6, I've just taken it from 1 to 100. Anyway, so the first thing you do is cancel out 1. So you know for sure that 1 can never be a prime. Now the algorithm goes this way. You select the first number which you haven't cancelled yet, and then this is your prime. This is guaranteed to be a prime. And after you have found a prime, then you start cancelling the multiples of this prime. So you cancel 4. So you cancel 4, you cancel 6, cancel 8, cancel 12, and so on until you get something like this. So the first step is clear, right, to everyone?
Yes.
Okay. Now the algorithm proceeds the same way. You find the next number which is not yet marked, that is 3. That is 3. And you call this to be a prime. And then you start crossing out the multiples of 3. There is no prime. 6, 9, 12, and so on until you have something like this. Now, what number should come next? Anyone?
5.
5, because 4 is already marked. 5, and then you cross out all the multiples of 5. That's possible, right? 10, 15, 20, 5, so on until you have something like this. Now you repeat this process. Next number would be 7, right? Then you cross out multiples of 7. 21. Okay, I'm not going to do all of this. And so on. Then 11 would come, and you need to cross out all the elements, all the multiples of 11. 22, 33, 44, right? All of those. So this is an easy task. Then 13, then 17, 19. Now, do you see the benefit of doing this? So at the end of the day, you would have this grid filled with either green circles or a cancelled right? Is that clear, everyone? So when you complete this for all the 100 numbers, each cell would be either crossed or would have a green circle around it. Now, the benefit of doing this is, now when I ask that is 19 a prime, you can tell just by looking at this grid whether it's a prime or not, right? You just see if this is encircled with a green circle or see if this is cancelled. If I say is 46 a prime, you can just see that, oh, okay, so I've marked this as not prime. So if you can do this on the entire thing, on this entire range initially once, then you can answer all of these Q queries in a constant amount of time. Any questions up to here? So is it clear?
Yeah.
Okay. Okay, so now observe that coding this is actually not that a difficult task. Basically, you just need to find the first location which is like neither cancelled not marked as a prime, and then you need to mark that as a prime and then cancel all its multiples that are bigger than this number. That's a very easy thing to code, right? So I've written a code of this over here. So this is prime is a boolean. So everybody knows what bool is, right? Anyone? Okay, so it's just either true or false. It's a data type for that. So I've kept a global array for this. And then I've initialized everything to true. And then I've like cancelled 0 and 1 because 0 and 1 are not primes. Then I've done the crossing out algorithm, this crossing out thing. So I start with 2 and I go to the upper limit. So my range is, let's say, 2 to max and minus 1. Then I check if this is marked as a prime. I'll come back to why this is sufficient. So if I get that this is a prime, I just start marking from I into 2 the multiples of I that these all are not prime. Okay. So this is same as cancelling. And in the next step, you get the I which is not yet cancelled. Not yet cancelled. So this must be a prime. Is the entire algorithm clear by now? I don't think it's very clear. Okay, so instead of putting green circles, you can imagine that I am picking the is prime thing. So I'm picking the is prime thing, and then for cross, I'm crossing the is prime thing. So if initially everything is marked with a tick mark, I only need to cross stuff. I don't need to retick stuff, right? I hope this is clear.
Yeah.
Okay. Okay, so this is the part where you tick, and this is the part where you check if this is ticked, and this is the part where you put a cross on it. So for all multiples of the prime that you just found out, you cross out all its multiples. So anyway, can someone tell me the complexity of this thing? Anyone? Just have a look. Sorry. The voice was not
N log n.
audible. Order n log n, right? Why order n log n?
The inside loop is running for almost n by I times, and the outside loop is, so it is n into 1 plus 1 by 2 plus 1 by 3 till.
Something like this you are saying, right?
Yeah.
Estimate of the actual runtime. But the thing is, this is not a factor, like this is not a summand in the final expression, because you're guaranteeing that I is a prime. So right. So you only have something like n into 1 by 2 plus 1 by 3 plus 1 by 5 plus 1 by 7 plus 1 by 11, something like this, right? So n by I is a prime.
It is n log log n.
Exactly. So it's n log n according to, I mean, you can prove this using the theorem I stated over here. This is called the prime number theorem. But like, let's not go into this.
Could you explain the code little in a detailed?
Okay. Let me do one thing. Let me run this code by hand for this grid. Can I paste this thing? Okay, let's keep it here itself. Maybe we can shift this circle. Okay, I won't be crossing 30, 40. This might not be a good idea. Okay, it's better like this. Okay, so what I'm initially doing is encircling all of these. Let's do up to 20. Okay, so this is this part. This part is clear, right? Okay, I have used very like this is not at all a C syntax. I would write it like this. Okay, so was this the only problem? Okay, I'll just run over the entire code once again. So this should be like this something. So it basically initialize everything to true. So by true, I'm representing green circles, and by false, I'll be representing it by, let's say, a red cross. Now you cross 0. So 0 is somewhere over here, and 1. Okay. So this part is clear, right, everyone?
Yes.
Okay. Also do tell when it's not clear. Okay. Now you are starting from 2 and you are increasing it up to 20, let's say. Now, if you see that this number I is already marked with a, so I'll just erase this green circle around 1. So for I, if I see that if I is encircled with a green circle, then I know that it's a prime. Okay. And then I start marking the multiples of I as not prime. So 4, 6. So I is 2 in this case. So up to this, it's clear, right?
Yes.
Okay. So this part for 2 is done. Now you come in with I equal to 3. You see that it's marked as a prime. It's encircled with a green circle. So you know that it's a prime. And you start crossing its multiples. So you cross 6, you cross 9, you cross 12, you cross 15, cross 18. That's it. So this part for 3 does this for you.
Okay, got it.
Okay. Now when I comes with, let's say 4. Okay, so when I comes with 4, this if statement is not satisfied because you have marked I as not prime. That is, you have cross mark. So you do nothing for 4. Okay. Now you move on to I equal to 5. You see that it's marked as a prime, that is, it's circled with a green circle, and then you start marking its multiple as not prime. And you do this stuff for 7. So for 6, you see that it's marked as not a prime, so you do nothing. For 7, you again mark 14, and so it's just 14 as not prime. And then for 11, you don't have to mark anything. For 13, you don't have to mark anything. And for 17, 19 also, you don't have to mark. So I hope it's clear by now. Anyone has a question? Okay. So with this initialization, you can answer every query in like constant amount of time. For I equal to 0, I is less than equal to q plus I. Ci and p. Then check if is p is prime of p is true, then you print yes, otherwise you print no. That's it, right? Okay, so I'm not getting any response. I hope this is clear.
Yes.
So the point I'm trying to make is this part is for initialization. So here the algorithm would be initialize everything with sieve. And then let's say process each query in, what should I write it over here? Anyone?
Constant 1.
1. Yeah, constant. So process every query in constant time by just checking if is prime of p is equal to true or false. So this algorithm gives you order. So what is the order of the entire algorithm? Just in terms of q and p maybe. Can anyone tell? So this is p and this is q. The order of the entire algorithm is anyone?
QP log P.
That would be worse than this, right? Look, the observation is you initialize it only once.
Yeah, sorry.
And then you process Q queries. So
P log P.
P log P plus Q into O of 1.
P log P plus Q, Q into O of 1. So this is the final complexity, right?
Yes.
Is everyone convinced?
Yes.
Yes, sir.
So this would be 10 to the power 9 with very heavy compute, with very heavy operations. So this would not pass the time limit, but this would easily pass the time limit. Just code it once and check.
But Q can be greater than P, no? Like, hello.
Yeah, Q can be greater than P.
Then we should take the higher number, no? Then it will be O of Q now when it is greater than P.
Yeah, that is why I've written both of them.
Oh, okay, okay.
Yeah, obviously. So if P is of the form 100 and Q is 10 to the power 6, then of course it's same as order P, order Q. So, I mean, okay, so an exercise from the complexity class. Can you prove this thing is equal to order of max of m comma n? Try proving this later. Okay. Okay, so I see that we have already hit 7:30. I was intending to cover some more topics where divisions would be covered. Okay, we can have a part 2 of this maybe later on. Okay, then I think we will stop over here. So any questions regarding the entire session? Anything?
Will modular multiplicative inverse would be covered in this, that is binary exponential and other things?
Yeah, that like I did plan to cover it in today's class itself, but yeah, I ran short of time. So I think there will be a part 2 where I would cover this modular inverse, multiplicative inverse, and then I would cover some more topics which are not in these set of scribes, like matrix multiplication maybe. But sorry, I couldn't make it to the end for this class. Anyway, we will have part 2 for this, so don't worry.
Sir, any references for CP?
For any references for CP?
Number theory.
For number theory. Okay. So for the mathematics part of number theory, there is this book by David M. Barton, I guess. David M. Barton. This is a very standard book. It's called Elementary Number Theory, yes. And like PDF version of this is available. And for problems and topics, and for problems, you can always search in code forces. So everyone over here knows about code forces, right? Anyone? Okay, so how many of you know about code forces? Can you raise your hands?
How many know or how many don't know?
How many of you know about code forces? Okay, so most of you know about code forces. So there is this platform called codeforces.com where you can find problems by some topic. So that's not the reason it's famous for. It's famous for its contests and blogs. So what you can do is go over to problem set and then add tag and search with this tag of number theory. So you will get a lot of problems in number theory. This is a good reference of problems. And for theory, I think like for CP theory in competitive programming, you can read various code forces blogs. Maybe there is this site called cpalgorithms.com. CP algorithms. So this site has many articles on number theory. Many of them are very advanced. Many of them are quite basic. So you can visit this site. I hope that answers the question. Any other question / comment / suggestion?
Up to what extent do they means like like what is the level of maths which they ask in CP, like in overall?
That is a very general question. I mean, for problems rated 30 to 100, they can literally ask anything from research papers. That's a very open-ended question. For division 3, for number theory part, I think up to modular inverse and Fermat's theorem, it should be enough. But yeah, there is no end to it, and there is no hard and fast restriction that, okay, you cannot use this because this is out of the syllabus. I mean, you don't need to worry about it much. Whenever you see some topics, you will get a rough idea of what all topics are asked in competitive programming. Anyway, I don't think that was a very satisfactory answer, but yeah, that's the best I can do. Any other queries? Okay, then I think we can call it a day. Also, next session would probably be on Wednesday, I'm not sure. Moinak, do you want to say anything?
I mean, about the date of the session, I mean, we haven't decided for sure, but probably
Yeah,
Wednesday. Yeah.
I think it would be on Wednesday or worst case Thursday or Friday. But yeah, you would be informed in Teams as well as Facebook. So everyone is following the GOC Facebook page, right? So you will get updates over there and in Teams as well. Okay, then if no one else has a question, I can end the class, I guess.
Thank you, sir.
And don't call me sir, I'm a secondary student. Yeah.